But tonight we've got the pleasure of Rob Erskine joining us from Glass Futures. For those of you that don't know, Glass Futures is creating a global centre of excellence for making glass that's low carbon material, which is going to aim to reduce cost, improve some of the challenges with regards to deployment for innovative glass solutions in our supply chains. This new Centre of Excellence is currently being built in St Helens, and I've got no doubt Rob is going to tell us all about it. But this pilot facility really is starting to bridge the technology readiness level gap, so getting us from university innovation levels up to industry level innovations. Rob is responsible for the oversight and deployment and development of Glass Futures projects, and is responsible for the innovation roadmap. So it's really great that we've got you here tonight to show us what this path is going to look like for Glass Futures and what we can expect looking forward. It's worth mentioning that Rob's got 26 successful funding applications, which have secured more than £28 million in grant applications. So that's huge and really puts you in good standing for what we can expect from Glass Futures. But one of the most prestigious awards that you've been given most recently is from the Society of Glass Technology, and that's the Alistair Pinklington Award in recognition of excellent work in glass research. And it's my great pleasure to welcome Rob to the SMEA to tell us all about Glass Futures and their vision. Over to you.
Well, good evening. It's great to be here. Thanks for the introduction, Colleen. So just again, a bit more of my background. Studied material science and metallurgy in Cambridge for my degree. I then joined Chorus, but then became Tata Steel. So it's great to see some of my old colleagues here today. So I spent 8 years working at Tata Steel and became an expert in watching paint dry. That was my claim to fame at Tata Steel. And then I the glass industry in 2012. I joined British Glass in their technical division called Glass Technology Services, where I headed up their innovation and projects department. And it was while I was there that I got developing this concept that is now Glass Futures, which I'll talk about later on. So I've actually been involved in Glass Futures now for about 6 years. I joined full-time in Glass Futures just after it became its own individual company about 3 years ago. So I'd like to start just by kind of introducing Sheffield's rich heritage in glass making. Most people know Sheffield as a steel city, but actually Sheffield has a really big heritage in glass manufacturing and glass science and research as well. So glass has been made in Sheffield for hundreds of years. So in the right-hand corner there, you can see the glass kiln, which you can find in Catcliffe, that's near junction 33 of the M1. In Rotherham, just down the road, we actually have the longest operating or continuous operating glass manufacturing site in the UK. So it's now called Beats and Clark, so you can still see it today if you drive through Rotherham. Also, Sheffield is renowned for the research that it's done. In 1915, a chap called William Turner, Professor William Turner, set up the first glass manufacturing department of science here in Sheffield, in the University of Sheffield. And then in the top left-hand corner there, you can see a museum, the Turner Museum that was established in the 1940s. And then still there's an awful lot of really good research and really good work with the glass industry that's done in Sheffield. So up in Chapeltown, you can see the building there. That is the home to the British Glass Trade Association, the Glass Technology Services, GTS Technical Services and Consultancy Group, as well as the Society for Glass Technology, which is also based in that building. So Sheffield has a rich heritage, and it's still got a lot of glass research and manufacturing, even in the present. So I thought I'd start by asking a bit of a question, if I can change the slides. So what I've got here is a number of different photos, and the question is, which of these photos doesn't contain anything containing glass? And people from Glass Futures aren't allowed to answer because they know the answer. Anyone want to hazard a guess? Oh, you got it straight away. Well done. It was a bit of a trick question. So basically everything else, apart from the spectacles in that bottom left-hand corner, contains in the image somewhere something that is made of glass. The spectacles, the reason they don't contain glass is because actually glass is quite heavy. So if ever you've had safety specs that are actually made of glass, you realise that it hurt your nose after about half an hour of wearing them. So that's why most spectacles actually are made with polycarbonate lenses. So there you go. But I mean, just to give you the different uses of glass. So obviously most people think of bottles and windows and tableware when you think of applications in which glass is used. But for example, mobile phone screens, they're made of glass, special glass called Gorilla Glass, ultra lightweight, very thin, very strong. I'm sure you've all come across the glass insulation you have in your lofts. Interesting, that's designed so that if you breathe it in, it dissolves in your lungs. It doesn't give you cancer. So interesting fact there. It's still not good to breathe it in. I wouldn't recommend it, but at least it's not that dangerous if you do. Interesting lasers. There's a lot of glass in lasers, not just the lenses. You can actually make the laser medium itself can be made out of glass. Interesting one is golf clubs. Actually, they banned metallic glass golf clubs because they were too good. That's often there. My glass friends often tease my metal friends on that one. And then actually, glass has a real part to play in terms of trying to improve the sustainability of our society. So you get glass in solar panels, obviously, but also, don't know if you know, but in wind turbines, you typically get over a ton of glass fiber, and the glass fiber reinforced polymers, composites that are used for wind turbines as well. And another nice one is the nail varnish. The little sparkly effect you get in the nail varnish, that's actually glass flake that gives it the kind of shininess. And then in road markings, again, road markings actually put a layer of really tiny glass beads on the surface of the paint, and that's what kind of reflects the driving along. So it is actually the glass that makes road markings reflective. So you can ask me about the other applications later, but I won't bore you anymore. So despite the fact that glass is used in a whole host of different applications, the majority of the glass that is made, particularly in the UK, is made primarily for glass containers and for flat glass that's used in applications such as windows and car windscreens. There's a little bit of fiberglass. Some of that's the continuous fiber for fiberglass, but most of the rest of that is for like loft insulation and wall insulation as well. There's actually a surprisingly large amount of glass that is made in the UK each year. So approximately 3.5 million tons of glass is made each year. So it is a significant industry. Interestingly, you can see if you look at the kind of map, this map shows where all the major glass manufacturing sites are. And they're actually really concentrated along the M62 corridor. So mostly in Yorkshire, but also a few the other side of the Pennines. And apparently that's because of the combination of really good coal reserves and lots of the right quality sand. So you can't just use any sand for glass. You have to use quite high quality sand. Apparently, historically, there was lots of that sand available. So interestingly, that's where all the glass is around. So we are really in the capital of glass. So glass itself is a very energy intensive process. Obviously, you've got to melt the raw materials. So the primary raw materials are sand, limestone, and sodium carbonate. So you have to mix those together with some other additives and hopefully a lot of recycled glass. You have to heat them up to around 1500 to 1600 degrees in the furnace to get them to melt and dissolve together. And then they come out at the end and you can actually form it into the final products. So all that uses a huge amount of energy, but as well as carbon dioxide generated from the predominantly natural gas that they use in the furnaces. There's also actually a lot of carbon dioxide that's given off from the decomposition of the raw materials as well. So if you think of limestone, that's calcium carbonate, and the sodium carbonate, as they dissolve into the glass, into their oxide form, the carbon dioxide is released. So as well as, if you look at the kind of overall carbon emissions from making a ton of glass, you'll see that about 58% is actually just from the combustion of the natural gas in the furnace. A further 18% will be from the decomposition of the raw materials. And actually then another 25% is actually what we call scope 2 emissions. So that's carbon dioxide that's generated from the production of the electricity that's used both in the furnace itself, but also in the downstream manufacture of the glass products. So all in all, just that the melting process and the site emissions for making glass, if you add all of those up across the whole of the UK glass industry, that comes to about 1.5 million tons of carbon dioxide that's emitted per year. And then there's an estimated further 500,000 tons of CO2 that's released sort of in terms of those scope 2 emissions as well. So glass, whilst it has lots of positives for our society, there's also a negative there in terms of the amount of energy and the amount of CO2 that's required. And I'm sure you've all seen graphs like this that show that the fact that the temperature, average temperature around the world is increasing. So because of this, understandably, the glass industry is under a lot of pressure from its customers and from its supply chain to do everything it can to reduce those greenhouse gas emissions, in particular the CO2. I think the thing I want to stress is it's not just the CO2 that we need to look to reduce. Actually, what we want is a truly sustainable manufacturing industry. We don't just want to get rid of CO2 emissions and then mess up all of the land and the sea and destroy people's lives. We really want to have an industry that is sustainable in every aspect. So you can see here, these are the 17 UN sustainable goals. And as a glass industry, we are looking at this, really working through sort of how can we make sure that we're trying to address as many of these different goals as possible through our operations. I think this is kind of the reason why the vision of Glass Futures was born. So if you look at the glass industry, it's a big industry, but it is made up of quite a large number of different players. They're all often doing their own research. If you look at the nature of the glass manufacturing process, most glass sites will have maybe 1 or 2 furnaces. Those furnaces are huge. They'll have an output of sort of anything from between 400 tons of glass per day up to about 900 tons per day per furnace. And those furnaces have to operate continuously for up to 20 years. So you can understand why a glass manufacturer is a bit reluctant to trial out a new technology on their line, because if they do anything that damages that furnace or puts that furnace out of action for even a few days, then it will cost them a huge amount of money. So there was a real need within the industry to try and work out how do we help the industry, first of all, identify those key technologies that they need to become more sustainable. And then once we've identified them, how do we actually develop them and trial them? And I think that's where Glass Futures was born. We realized that each company on its own couldn't address the challenge. It actually needed a centre that all the industry could come together, that was neutral, that wasn't owned by a private company, where everyone could come together and kind of pool their resources, pool the ideas, and develop those technologies. So Glass Futures was born. The idea is that it's open access. It's a platform that anyone can access, not just from the glass industry, not just manufacturers, but everyone. And also it's not for profit. So the idea is that all the money that's invested goes to do further work and invest in the organisation. It doesn't go to shareholders. But it also means that we've not got sort of shareholders telling us what to do necessarily. Really do have a lot of flexibility in that. Yeah, so that's Glass Futures. And then in terms of our mission really is to try and identify those technologies that are going to give a real step change in performance. So if you look at the reduction in CO2 emissions of the glass industry over the last 50 years, the industry has actually done quite well. We've managed to reduce the CO2 emissions per tonne of glass produced by as much as 50%, which sounds good. But if you look at how that change has happened over the last sort of 5 to 10 years, that change has really kind of plateaued. So everything, all of the easy wins have been achieved now. So if the industry is going to reduce emissions and become more sustainable, it's really going to require some real new technologies, disruptive technologies. And again, that is the remit of Glass Futures, to identify those technologies and to help develop and prove them. I think the other thing I want to point out here is that we don't just want to make glass manufacturing sustainable. We actually realise that glass has an opportunity to make or to have really positive impacts across society. As we saw in those pictures earlier, glass is used in a whole host of applications. So as well as making glass itself sustainable, we also want to try and help the industry develop products and capabilities that will actually help others to become more sustainable as well. So for example, did you know that in standard double glazing unit, they've actually got lots of very nanoscale thick coatings on each pane of glass. You can't see them, they're transparent, but what they actually do is they reflect the infrared. So in colder countries like ours, they reflect the infrared back into the building. In hotter countries, they reflect the heat out of the building. So that actually has a big impact in terms of how much energy is required to heat the building or keep the building cool with air conditioning. And actually some of the calculations show that a double glazing window actually saves as much as 10 times as much energy in terms of keeping the temperature right inside the building as it does to manufacture the glass itself. So there's all sorts of really exciting applications where glass has an impact. And as Glass Futures, we want to help the industry exploit those as well. One of the key ways we do this is to try and encourage collaboration in all senses of collaboration. So if you look across the glass sector, it's actually quite interesting how little the different sectors of the glass industry work together. So even though we're all furnaces that are very similar to each other, when you the guys that make glass containers versus the guys that make flat glass and the guys that make glass fibers, there isn't a lot of interaction in terms of sharing kind of core technologies, particularly around the furnace. So that's something we want to encourage more of, get all these people working together, find out what's worked in one sector that can be applied to another. We also want to work cross-sector in terms of different industries as well. So again, if you look at a steel plant, if you look at a ceramics kiln or a cement plant, actually they're burning lots of natural gas as well to heat up refractory boxes to process their materials. So we want to encourage collaborations and networking across sectors. And then we also want to sort of bridge that gap between academia and industry. So for those of you that have ever worked in either academia or industry, I'm sure you'll have appreciated the kind of challenges of getting this kind of two sides to work together. Often academics want to kind of focus on exciting science and kind of focus on everything to the nth degree. Whereas if you look at the guy running his glass plant, they just want something that works and they want it there quick and they want it cheap and they don't want to take the risk. So what we're trying to do at Glass Futures is trying to bridge that gap to try and get both sides talking the same language. So industry can really take advantage of the amazing ideas and the great capability they have. Also that academics understand the challenges that industry are under, that they don't just need good ideas, but those ideas have to be financially viable and those ideas have to be thoroughly investigated before they can be put on a production line. And finally, Glass Futures has been set up with a global remit. So whilst we are in the UK predominantly at the moment, and most of our funding has come from the UK government, we've really been given this remit to try and every glass manufacturer around the world to join the cause to try and develop these technologies. And in essence, it kind of makes sense because if you look at the industry, most of the manufacturers have global footprints. They have many of the members that we've got within Glass Futures have manufacturing plants or customers in pretty much every continent across the world. But also, if you look at the actual fundamental aspects of the glass furnace, every glass plant has a furnace that's near identical. So again, it makes sense not just to do research in the UK, but to try and apply that around the world as well. So this next slide is a bit busy, but hopefully it just gives a feel for the broad range of different types of companies that have signed up to Glass Futures membership. Interestingly, we've got quite a nice balance across the different areas. Not only manufacturers and supply chain, we've got some really good academic groups working alongside us as well. And interestingly, we've got a lot of brands. I've been really surprised at how many of these international brands have really been keen to engage with Glass Futures. And the reason is because if you look at their footprint of their carbon emissions, actually the majority of their carbon footprint is from their packaging in their what we call scope 3 emissions. And obviously glass is often one of their preferred types of packaging. So they realize that if they're going to hit their sustainability targets that their customers are them to meet, then they have to work with the material supply, like the industry, to help the glass industry reduce their emissions. So that's why, interestingly, we've got the likes of Diageo and Heineken and others, and people like Velux as well from the windows, really working with us to try and work out how can they help us help their suppliers of their windows and of their containers to make them more sustainable. So we set up Glass Futures. At the heart of the Glass Futures vision is to produce and to set up a pilot glass facility. In order to trial a technology, you have to actually trial it and demonstrate it on an industrially relevant scale, so that when you stick it on a glass plant, you actually know that technology is going to work and you've minimized the risk that you're going to damage your glass plant. So this is why we're setting up a 30 ton per day pilot facility or mini glass production line in a facility that's currently being built in St Helens. The reason 30 tons is that even though it's kind of a lot smaller than some of the big plants that operate at, say, 900 tons per day, we've been working closely with a number of the most experienced furnace builders across the glass industry from many of our members. And they basically advised us that they're confident that if it works on a 30 ton per day furnace, they can then extrapolate those results using their complex models, so that they have confidence to take those results and apply them on their furnaces. But we've not just built a glass furnace mimics a conventional furnace. We've actually designed it so that you can bolt on pretty much any technology that you might want to develop for the glass manufacturing process. So we've got technologies looking at the furnace itself, obviously, also technologies looking at dealing with the emissions, so things like waste heat recovery, carbon capture. Then we also set the furnace up so that it can run off a whole range of different fuels. So if you think back to the picture that showed sort of where the different levels of CO2 emissions that are produced by glass manufacturing, the majority were actually produced by the combustion of natural gas in the furnace, which is why we set this site up so that it can actually run off of low carbon fuels, such as biofuels, electric melting, and hydrogen as well. So this is what it looks like at the moment. So it's still being constructed, but they've all just about finished the actual building itself. It's actually based next to the St Helens Rugby League Stadium. And hopefully this kind of aerial view that you can see here just gives a feel for the scale of the facility. So whilst 30 tons is small for industry, it's still a pretty big site. I'm looking forward to moving into it hopefully next month. And then over the course of the next probably 9 to 10 months, we're actually going to then be commissioning or installing and then commissioning our glass furnace. So this is what it looks like from where our canteen will be. So this is actually the mezzanine floor, so it's not even the first floor. And hopefully this time next year, if you look out of that window, you'll actually see glass products flying off the actual line. So the line itself is actually able to make, or hopefully we'll be able to make both flat glass sheets and containers as well. So they'll kind of start at the far end where the furnace will be, and then the process will sort of come towards, standing looking at this picture here, and then there'll sort of be the forming and then the inspection at the end, and then it'll be taken off here. That's where the furnace is going to go. So this is at the far end of the picture that you were just looking at. So there's actually a hole here, which is where the furnace will go, and then this hole here is where we're going to have our container forming sections. It's a little schematic of the furnace. So it's sort of, for anyone that knows what a glass furnace looks like, you probably recognize it. So you've basically kind of got this is where the glass will be, and then this is what you call the crown. So it's arched. So it's basically kind of refractory box. The raw materials will be fed in the back end, and then they'll kind of come out this end. We're going to what's called a forehearth, where the glass is then kind of conditioned and the temperature's equalized. Then it'll either kind of be fed through a roll plate line or fed into the container section. Interestingly, what we tried to do is we tried to design it so we can test things like different refractories as well. So there's a little pocket here, and the idea is that we can put sort of novel refractories in there, so we can test how refractories, for example, might cope when the furnace is fired on hydrogen, because we know that that might pose a challenge to the refractories. So the idea is you can stick them in there, you can see how the refractories perform, you can then seal that area off, drain it, take refractories out, put new refractories in. I also design it here so that rather than the exhaust just going straight out through the chimney, we can actually kind of divert it through different pockets, either again to assess different refractories or to do things like looking at waste heat recovery technologies or carbon capture. So that's the schematic of what the furnace will look like. As well as the actual furnace we're building in St Helens, we've also developed another combustion asset. So this is actually based on the Brinsworth strip mill, Liberty Brinsworth strip mill site. So not too far away, just opposite the Magna Science Park. So this is what it looks like. It's quite a big facility. Basically, it's like a scaled down version of the furnace. So we don't actually put glass in there, but it is designed to simulate a furnace and the burner technologies that you put into a furnace. And it's got some water-cooled pins at the bottom, which you can just see as the darker areas in that picture on the bottom there, to basically kind of draw out the heat to simulate what you would get if you actually put in raw materials through there and putting glass out of the furnace. So again, this is really there to try and understand some of these alternative fuels, understand how they combust, how you optimize the flame, how the heat is transferred from the flame into the hearth or into your equivalent of the molten material, and then what emissions you get as well. So the idea is that you can kind of test your burners, you can optimize them before you actually go onto a furnace, or you can work out sort of the differences of the fuels and how they perform. So there are assets, the test equipment we're building. I'm now going to move on to talk about some of the actual research we're doing with these assets. What we've got here is the key areas where we think that as an industry we need to focus in order to truly make our glass industry sustainable. So we think if we can really address these 6 areas, we'll probably achieve most of the kind of, certainly the low-hanging fruit in terms of kind of taking out the kind of biggest amount of CO2 emissions and trying to make our raw materials sustainable as well. So I'm sure most of you have probably heard of these. So low carbon fuels, already looked at. So hydrogen, biofuels, electric are the prime candidates there. We're doing some work on carbon capture, which I'll talk about later. We're doing a bit on raw materials and recycling, looking at new raw material compositions. And interestingly, we're also doing a lot on what's called Industry 4.0. So this is basically kind of a catch-all term for anything related to kind of digital computing technologies, sort of computing technologies that are used to kind of control processes. Because actually, if you look at most manufacturing processes, there's a lot of waste, and often they use a lot more energy than they need to. Usually because one way to avoid something going wrong is to kind of overfire the product, because then you know that it's definitely properly melted or definitely properly sintered. But actually, with some of the new process control technologies that have been developed today, actually you can control your process so you don't need to use as much energy, or so that you can spot sort of when a process is going out of line, so you can correct it before it starts making defects. So again, that's something we're doing quite a bit of work on. But I'm going to focus mainly now on the work we're doing onto low carbon fuels. So we've been quite successful in getting funding to do this work. So far, over the last 3 or 4 years, we've managed to secure around £8 million worth of funding to work with our partners and our members to investigate alternative fuels for the glass industry, but also ceramics and steel. And in terms of the fuels we've looked at, it's predominantly biofuels and hydrogen. However, we realised that actually there's not really one fuel that's going to satisfy every single furnace. So what we probably will be looking at is more of the hybrid option longer term as well. How can we kind of use a mix of fuels to get that kind of optimization of heat transfer versus the kind of performance and the melting performance and the other characteristics you need to get your final product. So for those who maybe aren't so familiar with hydrogen and with biofuels, just thought I'd give a bit of an overview as to what we mean when we do say hydrogen as a fuel. So in terms of what hydrogen is, it is literally just hydrogen molecules or H2 molecules. So they are everywhere. Where have you got water? Where have you got any organic materials? You've got hydrogen. So it is abundant and hopefully it will always be inexhaustible. It's also could be argued it's 100% renewable. So you can make it from water, for example. You can split that water into hydrogen and oxygen if you have an electrolyzer. When you combust the hydrogen with the oxygen, it forms water again. So totally renewable, no carbon involved as well. So no CO2 emissions in the actual combustion itself. Very nice and clean. Actually quite good if you're in a remote environment. All you need is water and electricity and an electrolyzer. So you don't need to be kind of connected to the grid necessarily. You don't need to be tapped into a natural gas pipeline. Interestingly, hydrogen as a fuel is quite a good fuel. So it's got very high energy content. So that means that when you burn it, it does actually give off quite a lot of heat for what you put in. So it is a viable candidate to be used in industrial processes. And also, hopefully it can be transported via existing natural gas pipelines with a relatively minor changes to the actual gas pipelines. And also there's lots of government funding in there, which is good for people like us that want to research it. You might have heard that there's lots of different colours of hydrogen. Don't know if you've heard of that. Often on the news, they talk about different colours of hydrogen. I have to stress that hydrogen itself is colourless. So it's not like you get like these interesting coloured gases. But really the colour refers to how the hydrogen is made. Because depending on how the hydrogen is made, it does say a lot about how sustainable it is as a source of fuel. So that the colour is actually quite significant for industry. Ideally, we want either green or yellow hydrogen, because that's made from a renewable source. That's basically where you get electricity from a renewable source. You put it through an electrolyzer, which splits the water into hydrogen and oxygen. But you can also get hydrogen through other processes. The common one at the moment is what they call steam reforming. So that's not particularly great because basically you have to heat up some steam and you get your natural gas and then you break your natural gas into hydrogen. So it actually produces a lot more CO2 per unit energy than just burning the natural gas itself. But for research purposes, that's where we get a lot of our hydrogen from, just because we have to, because there's not enough green hydrogen out there. But you can also make hydrogen, for example, from electricity produced by nuclear energy. And there's also sort of other techniques that people are looking at, like pyrolysis gasification, where you basically kind of heat up either wastes or molecules or coal even, and it kind of breaks the hydrocarbons down into hydrogen and carbon. And particularly if you can then combine some of these with carbon capture, actually, even though you might be using natural gas or coal, actually there's still net zero in terms of carbon emissions. So blue is kind of like a good compromise in the short term while we build lots of electrolyzers. So hydrogen is good. I think it really has a lot of potential to be a future fuel for the glass industry. However, there's still a lot of challenges that we need to overcome in order to realise it as a fuel in the furnaces. And at the moment, one of the biggest is the economics. It's very expensive to make. It's also limited supply, so that's a bit of a challenge. Even for our pilot facility, we're struggling to get enough hydrogen just to run that. So you can imagine the challenges of running a 900 ton per day glass plant. There's health and safety challenges. So hydrogen itself, although it's been used in industry for many years, if a site's not used to using hydrogen, there are quite a few additional health and safety measures that are required. Hydrogen is very explosive. So if you're not careful, there is a risk there that you could cause an explosion. That said, it can be managed, and it is managed. So it can be safe. It just requires education of the workforce and new measures to be put in. There's also other kind of technical issues. So for example, when you burn hydrogen, you get a much hotter flame, which is quite interesting. Unfortunately, that then means you get more thermal NOx. So NOx emissions, the NOx is quite a nasty gas. Not only is it a greenhouse gas, but it's also really damaging for the human respiratory system. So really you don't want to produce NOx. Unfortunately, hydrogen has a tendency to produce more NOx, so that's something we're looking at mitigating. We're confident we can, but again, it's one of those areas that needs more research. And then also there's, as I mentioned earlier, we're not quite sure how it affects the refractories. So hydrogen itself doesn't necessarily affect the refractories. The issue is when you combust it, you get a very high moisture content in the furnace atmosphere that then interacts with the refractories, but also causes some of the components in the glass itself, like sodium and some of the sulfates, to volatilize. So then you've got a lovely kind of concoction of moisture-rich sort of sodium hydroxides, various sulfates in there as well, which many refractories don't like, and current refractories even dissolve quite quickly. So again, there's lots of work to do, lots of research that needs to be done. I mean, another one is actually hydrogen flames are invisible at high temperatures, which was a bit of a surprise to me at first. I kind of thought you'd be able to see it. But so interesting, on the left there, you've got like a nice luminous natural gas flame that you can see. But as you kind of start adding hydrogen into the natural gas, you move to 100% hydrogen, actually the flame disappears. So you can see it at cold temperatures, but in a glass furnace, you can't actually see it, which is a bit concerning because you can't actually see where the flame is. So sometimes the flame might kind of change direction or even impinge on the refractories itself, which is not good. So again, that's something we're looking at trying to mitigate. So that's hydrogen. Biofuels is another area we're looking at. I think biofuels also has a big potential part to play in terms of decarbonising our industries. So in terms of what biofuels are, basically it's like anything that comes from a bio-derived source. So it can be plants, algae, animals, or even kind of waste streams. So anything that kind of grows in some way or another can be used to make a biofuel. Common feedstocks of biofuels, things like woods, oils, waste oils, like cooking oil, vegetable oils, used quite a bit. Agricultural residues, so things like wheat straw or clippings from kind of trees and things. Also now there's a growing number of crops that have been grown as well, things like miscanthus and willow that kind of grow really quickly, grow on quite low quality soil. There's a lot of companies looking at growing those and then using those to then convert them into different fuels that can be used in industry or power plants. So biofuels are really good. They're renewable because obviously you kind of grow them, you cut them down, burn them, then the next plants that come up and absorb the CO2 as they grow. They're also good in remote areas. So there's particular interest in biofuels for industry, places like India or Africa, where they don't have great electricity supplies. They're unlikely to get hydrogen anytime soon. So actually biofuels actually provide a route to start decarbonising those industries in those countries in quite a short time frame. And actually, the interesting is one of the routes we're looking at is actually if you can combine biofuel combustion with carbon capture, actually potentially you could have a carbon negative glass manufacturing process. So actually in making your glass, you're actually sucking CO2 out of the atmosphere, particularly if you can then use it to use that carbon to make something else, like more raw materials. Other good thing about biomaterials is that the feedstocks are there in large quantities. So this little dotted red line you can see at the bottom, that is what we estimate to be the annual energy needs of the entire UK glass industry. And these bars kind of show how much biomass is available. So you can see that there's loads of biomass there. The challenge is how you actually convert it into a fuel that can be used in the glass industry. Again, we're working with various groups and university groups to try and work out how we do that. So whilst biofuels are good, they've got a lot of potential. Again, as with hydrogen, there are plenty of challenges that we need to overcome. There's a lot of technical challenges. So often biofuels, they might not be very clean. So some of the stuff that you get when you burn them can actually do nasty things to your refractories or potentially your glass. There's also a lot that needs to be done on the economics. So at the moment, the supply chains aren't particularly well established, certainly for some of the kind of lower grade, lower cost fuels. So we need to work on how we can actually make those more sustainable, or how we can actually maybe get them in a rawer form. Because one of the great things about a glass furnace is, because it's so hot or such a high temperature, anything you put in there will combust. So you don't need to refine it to a nice kind of high quality diesel-like product as you would for, say, if you're going to put it in a vehicle, you can actually kind of slap in stuff that's kind of pretty crude. But whilst that's lower cost, you get issues such as like variability in quality, which the furnace then has to kind of manage. And then also need to kind of do things like looking at things like emissions and the fuel stability. So many biofuels, they're not as stable as fuels like diesel. They can be attacked by microbes. If they get too hot, they can kind of gel or break apart. So again, that's stuff that we need to look at. Not insurmountable, but again, these are challenges that the likes of Glass Futures need to look into. One good thing about these fuels is they do burn really well. So this picture here is actually some data from our combustion test bed that I showed you earlier. So the green bars are the natural gas and diesel, so they were our benchmarks. You can see that even for a 20% hydrogen blend, we've still got quite good heat transfer onto that hearth at the bottom. And for some of the biofuels, they burnt really well. We've got even better heat transfer than for the diesel. So it shows that actually these fuels are viable. If you burn them in our glass furnaces, we're going to get good heat transfer. We're not going to get problems in terms of getting enough energy into the furnace. So they really do have the potential. So if we can overcome those barriers, then I think these are a route to decarbonise our glass industry. Interestingly, we have done a few trials. So these were with higher grade biofuels, so ones that aren't really economically viable because they're quite a lot more expensive per unit energy than natural gas. But we have actually run trials on both the container plant. So this was one container plant in Northern Ireland, in Derry Lynn. So we actually ran it for 3 weeks and produced over 4 million bottles. So I actually have some evidence here, just if no one believes me. So you can have a look at these afterwards. No drinking the whiskey, please. But yeah, see if you can spot the difference between that and a normal bottle. And the whole point is that you can't, because actually the glass that was produced met the quality standards for their glass manufacturing. So whilst the bottles look the same, the bottle here that you can see here that I'm holding up, sorry for those at home, probably can't see them, but you can see an example of it on the slide there. They've actually got, I think it was 95% less CO2 in the manufacture of those bottles than with a standard bottle. So shows it is possible. And then we also did one on the Pilkington float glass line in St Helens, where they ran that for, I think it was about 4 days, produced enough glass to cover 3 football pitches. Again, that was some of the lowest carbon that was produced, lowest flat glass that's ever been produced as well. So it is possible. We just need to understand how to do it better and more economically cheaper. So in terms of the different fuels, so this slide here is really just to kind of show you that there isn't really one fuel that kind of ticks all of the boxes. So if you look here, these are like little spider charts. So basically, the further out from the center that the point is, shows that it's got is better. So basically, higher score is better. So what we've done here, so if you can't really see it, but we've got kind of each the kind of key areas that we need to look at when we're trying to work out how suitable a fuel is. So everything from the availability of it, its CO2 savings potential, impacts on things like cost, melting efficiency, impact on the raw materials and the health and safety. So you can see the trouble is that each fuel might be strong in some areas, is weak, but might be weaker in others. Also with these maps, they change depending where the site is. So if you're kind of near the coast and you're in an industrial cluster, you might have access to hydrogen quite soon. So availability of hydrogen is good. If you're in Sheffield, maybe you might not get hydrogen for a bit longer. So availability is not so good. But again, over time, these will change. And it's really important to understand how the kind of preferred fuel might change over time. Because if you look at a glass plant, if you're building your furnace and it's got to last 20 years, you don't just want to look at 2030, because actually if some of the other fuels might actually be a lot better and a lot cheaper in 20 years time, you have to think, right, what furnace do I want to design? Perhaps I do need to design it so it can take or be upgraded to use hydrogen as well. So again, this is all the sort of questions that Glass Futures is looking at to try and help the industry make those kind of valid choices, not just looking at the technical feasibility, but looking at what's economically feasible as well. A bit on carbon capture. So if anyone that's not so familiar with carbon capture, basically it's a relatively straightforward concept. You basically get your emissions, your exhaust coming out your furnace, and you basically put it through a process that strips the carbon dioxide out of the emissions and then segregates that carbon and captures it. And then you can either use it to do something. So there's like various people looking at doing everything from using it to sort of put into greenhouses to help plants grow better, through to actually using it to create aircraft fuels. There's in fact the University of Sheffield at their site on the Advanced Manufacturing Park are looking at turning carbon dioxide into sustainable aviation fuels, which is really interesting. But within Glass Futures, our main remit is to understand what technologies can be used within the glass industry. So one of the challenges we've got within glass industry and many other heavy industries is that the emissions aren't just kind of air and carbon dioxide. They've got all sorts of other kind of interesting components in there, things like heavy metals, sulfates, NOx emissions that I talked about earlier as well. And those can damage the carbon capture unit. So there's a lot of work going on to try and develop technologies that can basically survive those kind of emissions and capture the carbon dioxide as cheaply as possible. So we've done a few studies there. We think that there are technologies out there that can capture carbon emissions from the glass industry, but it's probably going to be another 5 to 10 years before those are ready, particularly before they're ready at a scale where it's affordable, because at the moment the technologies use an awful lot of energy, which obviously adds to the cost, and also the CO2 if it's not green electricity. But interesting, we have found a company, Sea Capture. They're based up in Leeds. We do actually want to put a trial unit on our pilot line. So hopefully this time next year, we will actually have a carbon capture unit on our line. So we can actually then start to really understand how glass industry emissions impact those technologies. I also look at other projects to improve the sustainability of the glass industry. So it's not just the fuels. You actually have to look at the whole remit of the glass manufacturing process in order to get a truly sustainable industry. So we are looking at, as I mentioned earlier, things like digital technologies, look at new raw materials. So again, it's you can feel free to have a look at them later. But for example, this here, this little black glassy blob, that actually came out of a biomass electricity plant. So it was a clinker that was formed in the burning, I think it was of wheat straw. And what we did is this was when I was at GTS, so it's the GTS and Sheffield Hallam teams that did the work. But we took this material here and incorporated it into a glass and actually got quite a nice clear glass. So feel free to have a look at that afterwards. That's just one example where we've taken a waste that would have just gone to landfill, and we've actually turned it into a raw material that actually replaces some of those carbonates that are used in glass making. So that's just one example of of how actually, if we kind of take a step back and look at all the different opportunities across industries, we can actually find some really novel solutions of reducing waste and saving emissions in another sector at the same time. So just on that, in terms of those cross-sector bits of work that we're doing, so whilst we're Glass Futures, we've actually been given a remit by the government as part of our funding to actually make sure we're sharing that knowledge across other sectors as well. So we have done a lot of work with the ceramic sector and the steel sectors, and we've also got links into the cement and energy sectors as well. And we've also got a project with some advanced chemicals looking at using waste heat to drive some of their processes in terms of manufacturing their components. This here is some photos that were taken from our combustion test bed last year. So we actually did what we believe is the first ever firing of industrial ceramics products using 100% hydrogen. So we actually did 2 sets of trials, one on natural gas, and then we fired a second set of products on hydrogen. So you can see some of the things there. We've got obviously bricks. We've also got a plant pot there in the background and some nice plates and things. And subsequent analysis of the 2 sets of products showed that basically they had exactly the same performance. So it showed that firing these products on 100% hydrogen didn't actually affect any of the product properties. And off the back of that, hopefully in the next year or so, we're going to continue this work to actually do some industrial scale trials. And we're actually going to put hydrogen into some industrial scale kilns. So watch this space. And we also did the same for the steel sector. So this was part of a project called HIDES. So that was actually based in Sheffield, actually. It was a project led by E.ON. So I don't know if, I'm sure you've all seen the big power plant with the orange roof near Meadowhall. So they're looking at installing hydrogen electrolyzers on their site or investigating the feasibility of it. And they wanted to work out sort of which of the industrial users in that area could actually use the hydrogen. So they asked us if we could actually do some hydrogen simulation trials of the steel products from companies like Forge Masters, Forge Solutions, and Chesterfield Cylinders. So we kind of put various samples in our furnace and then basically fired them on hydrogen. And you can see we were able to get the thermal profile of some of these heat treatments really nicely profiled, even on the hydrogen. And again, we're still just finishing that project off, but the results do look really positive. And again, you've got examples of the burners. So that's the hydrogen burner at cold temperatures. So you can see the flame just about, but at high temperatures, you can't see it. And then another big project is a project called Economizer. So again, this is really more of a kind of high level project. And it goes back to the fact that we all need to work together. So what this project is doing, it's a £19.5 million grant from government. And it's really to get each of the different research groups across the different heavy industries working together to tackle some of these common themes that you can see here. So you've got Glass Futures, you've got the Centre for Process Innovation, which does a lot of work with the chemical sector. You've got Materials Processing Institute that focuses predominantly with steel and metal sectors, and Lucidian for the ceramics and refractories. And then they're kind of joined together by the Henry Boyce Institute. Again, there's a collection of the leading universities that are doing industrial research in the UK. So the idea is the 5 groups are going to work together to really try and sort of develop some step changes in these, but also to develop pilot facilities or research at scale, or that can do research at scale across each sector. So that sort of brings us to the end of the presentation. Just a few closing remarks. So I think, and I hope you would agree with me after this presentation, that we can achieve a sustainable net zero UK industry within the UK. It is possible. The solutions are there. However, it's going to require a lot of work. There's still a lot of research that needs to be done. And it's going to require a real buy-in and commitment, not just sort of across the supply chain. I think each of us as customers of these products who actually buy the bottles or the bricks, we need to be putting pressure on the industries to make sure that there's that incentive for them to do that. And I guess that to finish off with, do we have a choice whether we want to or not? I think we have to do this. So just to finish off, I'd just like to acknowledge all the various people that have been involved in helping to pull these slides together, but also to do the various projects. As you can see here, there's a big team behind me at Glass Futures, so I'm very grateful to all their hard work. And there's also a huge number of partners, and I probably missed quite a few as well. But you can see that we really have got great backing and support from industry as well. And I'd just like to extend a thanks to all of them as well. So thank you very much for listening, and please do let me know if you have any questions.
Fantastic presentation. Thank you very much, Rob. I certainly quite enjoyed the little bits at the start where you're talking about how small changes are going to have quite a significant impact to these manufacturers at an industrial scale. And I suppose it's quite scary to embark on some of those changes, and the opportunity that you're giving these industries is going to be second to none. Towards the end, you gave a really nice introduction to some of the biofuels, and it was quite nice to see that they're comparing rather well to one another, and to our standard, if you like. So it'll be very interesting to see what happens and how the industry is going to adjust to these changes. But I'll open the floor up to questions, and I'm going to play runner as well.
Just thinking about recycling and comparing to, say, the steel industry,
Yep.
What percentage of British glass production is from recycled glass, and what percentage is from raw materials? And are there any restrictions in what you can use recycled glass for? You know, can it just go into bottles, or can it go into float glass? Just interested to compare.
That's a good question. We've got half an hour. So, I mean, in essence, I think at the moment, the amount of glass that's recycled, I think, is in the kind of 60s or 70%, but then a lot of that is lost through the actual processing stream. So typically, I think, again, it depends on the color of the glass. So with green glass, you can kind of put lots of other types of glass into it. So they typically have quite high levels of recycled content, sometimes up to sort of 95%. Whereas for colorless glass, that's more challenging to put recycled content in. So for standard colorless glass, they can kind of push up to about 50%, depends on the quality and the contamination. But for really high colorless glass, then they might not even put any recycled content in either. And then it's kind of the added complication is things like with flat glass. So containers, they're pretty well recycled, but for flat glass, it's really difficult and expensive to get the windows out of the building. So that's something we're doing a lot of work with the likes of British Glass How do you actually incentivize getting that glass out and recycled? At the moment, a lot of it's just smashed and turned into aggregate. And also you've got like added kind of complications, which you wouldn't necessarily think about. But take flat glass, for example, they're really paranoid about where their recycled glass comes from, because if anyone uses stainless steel in the processing of that recycled glass, then bits of that stainless steel can get in, and it leads to this horrible defects called nickel sulfide, which are like almost too small to see, but then when they're up on a building, over time they kind of grow, and then it can cause the windows to kind of break. So if you think that you've got windows breaking at the top of skyscrapers, then that's quite costly. So there's all these, it's a very kind of complex dynamic. So ideally the industry wants to recycle as much as possible. So the challenge isn't that the industry doesn't want to recycle, because there's huge energy benefits and CO2 savings. The challenge is, how do you actually get that glass back to the furnace in good quality at an affordable price? Okay. Hope that kind of answered your question.
I've got loads of questions written down, so I can go straight to my list, but surely there's another one on the floor.
Yeah, sure.
The biomass, how much of the fuel is imported?
So at the moment, of the biofuels we've been using, they have been produced in the UK. So a lot of it has been from feedstocks like used cooking oils, and maybe a few from kind of plant wastes. I mean, when I actually went to a biorefinery last year, it was quite an interesting process. They kind of got all sorts of different feedstocks, and it kind of went through lots of different chemical steps, and eventually got this nice kind of liquid fuel that came out of it. So you can make it out of lots of different things. And the graph that I showed you was with the different kind of levels of biomass availability. That was availability in the UK. So there's plenty of biomass in the UK that can be used, and there's plenty of waste streams that can be used. So we're pretty confident that we can have enough, we can make enough fuel in the UK to source all of the industrial needs in the UK. But again, that's part of one of the things we're looking at, because like with any fuel, it's kind of quite hard to kind of control where it's produced and where it's used. So we're actually doing some work with a group called the Supergen Bioenergy Hub. So they've got some really kind of complex databases where they can actually understand what is the true sustainability of a fuel. Because what we don't want is, we'll take a fuel that we think is sustainable, but then that leaves kind of a hole in the market. So someone that was using that fuel can't use it anymore. So they then start buying a non-sustainable fuel that's made from something that's grown due to a rainforest that's been chopped down. So it's a really complex picture, but it's important to understand it, and that's one of the reasons we're doing research in it.
If I can take you to St Helens.
Yes.
So you've got a pilot facility that can have a throughput of up to 30 tons.
Yep.
What happens with the product at the end? Do you guys have the facilities to do quality assurance checks, or does it go back to whoever the partner is for them to do their own quality checks on it? And if it's of suitable quality, can it go into the market?
Yeah, so I guess there's a number of ways to mention that. It probably depends on the experiments we're doing. So with some experiments, we probably don't want the final product, or it won't be of suitable quality. So we'll just kind of collect samples, and then the rest of it will be like recycled back through the furnace as recycled glass. But what we do want is, certainly for the container line, is to ultimately have not just the forming section, but all of the inspection sections as well. So we'll produce the bottles, they'll get inspected, and then potentially could be used commercially. But we are kind of set up as a research facility. So those bottles, might not be good enough, or they're probably produced in quite small volumes. So it might be kind of specialist runs.
Limited edition, there's extra value there. Yeah. Ken, you had a question?
Every few weeks in our bins, I have metal and glass.
Yep.
And that's collected. Exactly what happens? Do they separate the glass from the metals?
Yes.
Yes.
Generally the recycling sort of facilities are quite sophisticated now, so they have quite good technologies that separate out all the different materials. That said, the amount of glass that you can actually get back to a reasonable quality from the curbside collections isn't as good as if you just put it straight in the bottle bank. So it's generally better to put it in a bottle bank, but the fact that many people wouldn't use a bottle bank means that the net benefit of curbside probably still is good. But if you look at some of the countries on the continent, like Netherlands, I think even Wales actually separate out the glass. If you go to parts of Wales, they actually have trucks and they have people separating out the materials, and you actually get a really high, much higher percentage glass collected in a way that can be put back in the furnace in those regions than the curbside. So whilst it is good, the recycling infrastructure is good with the curbside, it's not quite as good as separating it out at source.
Oh, fantastic. Got one at the back.
As you're recycling glass, as you go through each cycle, can you remove the additions that have been made, or do they build up through each cycle like they do in steel, like with residuals in steel? So if you can't remove them, do you have to dilute them by using glass without additions?
I mean, the advantage with steel is because it's amorphous, it kind of all gets mixed together. So the only real detriment really is to the colour. And therefore, if you're managing the recycled glass that's going in and you keep that to the right colour, then you're unlikely to get any additions. The only exception is potentially lead. And that's sort of historically used to get kind of like lead crystal and cathode ray tubes would get into the recycling infrastructure. But there's now a lot less lead glassware produced. So obviously people don't have cathode ray tubes in their televisions, and also even lead crystal now. A lot of the new products that are produced for the tableware market are made with lead-free materials. So you do get some build-up, but it's nowhere near as big a problem as in steel. It's mainly the colour is the big issue, and as long as you can, yeah, it doesn't affect the mechanical properties at all.
I've got one more, if I may.
Okay, cool.
At St Helens, we've got this facility that allows you to change different processes or your approach towards it. What's your anticipated downtime between different partners working with you on this?
So once we've what we say, we lit the furnace, which means when we've got it up to temperature, we want to try and keep it running as long as possible, because whenever you cool a furnace down, all the refractories kind of expand and contract at different rates, and it damages the furnace, and it's never quite as good. So what we're aiming to do is basically line up our experiments so that we can run it for as long as possible once we've run it, once we've started it or heated it up. So I mean, our ideal is that we'd run it continuously for a couple of years. In practice, we might sort of run it for 6 months and then have to cool it down and change things. But that's what we'll do. So the idea is we'll kind of have it such that we can just kind of run one experiment after another. And if you have to change anything, either change it while the furnace is hot, which apparently is possible, or like things like composition, we kind of design it so we can flush out the previous glass as quickly as possible, so that we've then got the new composition coming through without it having to run too long.
Brilliant. Sounds like you've got all the answers. If we could thank our speaker again tonight for a fantastic presentation.
Cool.